Welcome to the deep end. Today we are mastering cache architecture and data inconsistency. If you're building for scale, this is where the engineering gets real. Don't forget to hit like, share, and subscribe to support the channel. Also, head over to www.bitbytoken.com. It's your ultimate resource for foundational and advanced system design across software, data, AI, and ML engineering. If I were to give you a brief walkthrough of the site, these are the various disciplines that we have: software, data, machine learning, and AI engineering. Each of those disciplines are further have fundamentals which are searchable. Um, in case you want to search for anything like indexing, basics, advanced, and experts. And then we have sample solutions for each of these. Designing Twitter, Instagram. We have to try to make them as comprehensive as possible. Um, you can navigate through functional requirement, non-functional. We have data model, sequence diagrams available for each of these functionality. We are also talking about various scalability, availability options, sharding, scaling, and then trade-offs and consideration, which are very critical for any system design uh, decision. Okay, let's get into our topic for the day today. Okay, so we start with the Speed-Truth Tradeoff Matrix. Remember, no caching strategy is universally best. It's all about the balance. We have the right landscape where you choose between strong consistency and low latency, and the read landscape which balances complexity against staleness. The right choice between like depends purely on your application's tolerance for stale data and your read to write ratio. Respect the physics and choose your trade-offs wisely. Right behind is the art of deferred truth. It's an incredible pattern for surviving massive write spikes without melting your database. In step 1, the client writes to the cache. In step 2, the cache acknowledges immediately. The client is completely decoupled from the slow database latency. Finally, in step 3, a background process drains the queue and persists changes asynchronously. It's high performance, but changes how you think about durability. The secret power of right behind is batching and coalescing. Imagine 10,000 individual queries coming in. Coalescing allows us to drop intermediate states. If a user updates their card 3 times in milliseconds, we only process the final state. Then batching collects those writes into a single bulk operation. 10,000 individual queries become one single bulk update, significantly reducing the load on your database layer. However, right behind has warning zones. Risk 1 is the data loss. If the cache crashes before the flush, those writes are gone. Mitigate this by using a durable message queue like Kafka for your write queue. Risk 2 is dirty reads. If service B reads the database directly while the truth is still sitting in the queue, it sees stale data. The golden rule: never use this for financial transaction. Reserve it for high volume analytics or view counts. Now for the catalyst, the thundering herd problem. This is the broken state of traditional TTL caching. When a highly popular key expires, the cache empties, and thousands of concurrent requests, the stampede hits the database at the exact same millisecond. The result is often a cascading system failure. This is exactly what we have to prevent in the high scale systems. To solve that, we use refresh ahead or proactive prefetching. Instead of the client waiting for a sync read at the cliff of the expiration, the system triggers an asynchronous background refresh as the TTL nears its end. The client always gets an instant response from the cache, and the expiration becomes invisible. The client never experiences database latency. How do we tune the refresh factor? Think of this. Uh, think of this as the thermostat of your system efficiency. The sweet spot is typically zero point 0.5 to 0.75. If it is too low, you burn DB resources refreshing data that might not be accessed again. If it is too high, you risk missing the window entirely and falling back to a synchronous cache miss. Tune this parameter based on your specific traffic patterns. Invalidation is famously the hardest problem in computer science, or infamously, if you will. The scenario is simple. The database updates instantly, but the cache serves stale data until the TTL expires. When the CO calls because the price on the app is wrong, you need a strategy. We analyze this across three dimensions of consistency: timing, scope, and the mechanism of the invalidation itself. Strategy 1 is time based or TTL. It's the ultimate simplicity. It requires zero extra infrastructure and acts as a mandatory safety net for all other strategy. The flaw, however, is that it's time billed to actual database changes. It's best for static content, user profiles, or nightly reports where some staleness is perfectly acceptable. Strategies 2 is event-driven invalidation. Here, database changes trigger immediate events that actively delete or overwrite cache entries. Its superpower is near instant consistency. The risk is the do or write window, a tiny gap between the DB update and the cache invalidation. It requires complex event bus infrastructure like Kafka, but it is perfect for price updates or inventory counts. Strategy 3 is version based O1 magic. Instead of trying to delete 10 million keys, you simply increment a global version number embedded in the key path. The old keys are orphaned and naturally expire via TTL. It's a brilliant way to handle bulk invalidation atomically. Just be careful. If that version key itself expires from Redis, the version might reset, resurrecting ghost entries. Now, when it comes to advanced stampede protection, we have three powerful countermeasures. 1. Log-based refresh, where only one request rebuilds the cache. 2. Probabilistic early expiration, which spreads the load over time. And 3. Stale while revalidate, where you serve the stale data immediately to block the herd while asynchronously fetching the fresh data in the background. Now, synthesis, this is the hybrid MAANG architecture. In production, no single strategy works alone. You layer them. Right behind queues for telemetry, refresh ahead for hotkeys, event-driven buses for precise updates, and versioning for bulk operations. And above all, you keep an absolute TTL as your safety net. This is how you build systems that don't break under pressure. Finally, remember, a cache you cannot observe is a time bomb. Keep a close eye on your hit rate, your write queue depth, and your invalidation lag. Before you design, always ask, what is the acceptable staleness window? What is the read to write ratio? And what is the blast radius of a failure? Thanks for watching this deep dive. What is the most difficult cache consistency issue you have ever had to debug? Let me know in the comments below, and don't forget to like, share, and subscribe. Until next time, have a good day.